3. Iphiatlas is an interstellar object, meaning it came from outside our solar system. It is only the third such object ever seen passing through our neighborhood of space. The first was 1I Oumuamua, spotted in 2017. The second was Comet 2I Borisov, discovered in 2019. These earlier finds surprised scientists and sparked new interest in searching for visitors from other star systems. 3 Iphiatlas continues that story, adding to our understanding of how objects travel between stars and what they are made of. Astronomers first noticed 3 Iphiatlas while tracking faint moving points of light in the sky. At first, they thought it might be a comet from the outer reaches, but its speed and path quickly showed it was different. Objects bound to our Sunday follow certain curved orbits. 3 Iphiatlas, like Oumuamua and Borisov before it, travels on a hyperbolic trajectory. This means it is moving fast enough to escape the Sunday's gravity entirely. It came in from deep space, passed near the Sunday, and will leave forever. This kind of path is a clear sign that the object is interstellar. The name 3I Iphiatlas carries, meaning 3I shows it is the third recognized interstellar object. The Atlas part comes from the survey that found it, called the Asteroid Terrestrial Impact Last Alert System. ATLAS is a set of telescopes designed to spot small objects, especially those that might one day hit Earth. In this case, it caught something much rarer and more distant. The speed of 3 Iphiatlas is very high, even compared to other space rocks. This is expected for something that began its journey around another star. Imagine throwing a ball from one moving car to another. The speed adds up, and the ball moves faster than it would from a single car in space. Stars move too. A rock ejected from a distant star's gravity can gain great speed before it even reaches us. 3 Iphiatlas travels fast enough that no gravity here can hold it back. Scientists are especially interested in what 3 Iphiatlas is made of. Material from another star system could tell us how planets and comets form elsewhere in the galaxy. With 2 Iphi Borisov, astronomers saw gas and dust typical of a comet, suggesting it formed in a cold, icy region like our Kuiper belt. Oumuamua was stranger. It looked more like a rock than a comet, with no clear tail or gas cloud. It also had a curious shape and odd motion that sparked many theories, including some wild ones about alien technology. Most experts think it was a natural object, perhaps a shard from a broken planetesimal, though the exact details remain unknown. 3 Iphiatlas adds new mystery. Its brightness changed in unexpected ways, hinting at an unstable surface or unusual rotation. The color and spectrum of its light suggest it might contain frozen gases, like a comet, but the pattern does not match anything seen before. This mix of comet-like and asteroid-like features makes it hard to classify. It could even be a hybrid, perhaps an icy body that lost much of its ice while traveling through interstellar space. To study an object like this, astronomers use many tools. Ground-based telescopes track its position and motion, measuring how sunlight reflects off its surface. Space telescopes, free from Earth's atmosphere, can capture fainter details and view it in infrared light. Spectrographs break the light into a rainbow of colors, revealing chemical fingerprints. From these data, scientists can estimate the object's composition, spin rate, and even its rough shape. They cannot touch it directly, so every clue must come from light alone. If we imagine 3 Iphiatlas up close, it might look like a dark, irregular rock covered in frozen patches. Some parts could be smooth from past melting and refreezing, while others are rough and pitted from impacts. As it approaches the Sunday, any remaining ice could sublimate, turning directly into gas and creating a thin halo. This halo might not be as dramatic as a typical comet's tail, but even a faint one tells scientists about its makeup. The path of 3 Iphiatlas through the solar system was brief. It entered unseen from the cold darkness between stars, passed inside the orbit of Jupiter, then swung past the Sunday and Earth before heading out again. During this short window, observers worldwide worked around the clock to gather as much information as possible. Once it leaves, no one will see it again. That urgency drives teams to collaborate across countries and observatories, sharing data in real time. The discovery of 3 interstellar objects in just a few years suggests that such visitors may be more common than once thought. For most of history, our telescopes were not sensitive enough to detect them. As technology improves, we are likely to find more. Each one is a messenger from another system, carrying physical evidence of processes far away. By comparing them, scientists can piece together how common certain materials are and how often objects are ejected from their home stars. Imagine a young star surrounded by a disk of gas and dust, like our Sunday was 4.6 billion years ago. Within this disk, clumps grow into planets and comets. Some of these bodies collide or are thrown outward by giant planets. A few are ejected completely, flung into interstellar space. They drift alone for millions or even billions of years before chance brings them near another star, ours. In this case, 3I Phi Atlas may have been part of such a story, launched long ago by forces we can only infer. For people on Earth, these objects are harmless. Their paths rarely come close to our planet, but they provide a unique chance to study matter from far beyond our solar system. Without leaving home, each observation helps refine models of planetary formation and the distribution of material across the galaxy. In this way, 3I Phi Atlas is like a sample return mission. Only the sample came to us on its own. The future of interstellar object research looks bright. New surveys, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, will scan the sky with unprecedented detail. With these tools, scientists expect to catch many more such visitors. Some may even be identified early enough to consider sending a spacecraft to intercept them, capturing close-up data that telescopes alone cannot provide. Until then, objects like 3I Phi Atlas remind us that our solar system is part of a much larger galactic environment, full of wanderers crossing the spaces between stars. The Great Filter is an idea that tries to explain why we have not seen signs of advanced life beyond Earth. The universe is vast. There are billions of stars in our galaxy alone, and many of them have planets. Some of those planets are in zones where liquid water could exist, making them possible homes for life. With so many chances, it seems like we should have seen evidence of other civilizations by now. Yet, we have not. The sky is silent. This puzzle is known as the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" The Great Filter is one possible answer. The concept of a filter is simple. Imagine a long path with many gates. To reach the end, you must pass through each gate. If most travelers fail at one particular gate, very few will make it to the end. In the case of civilizations, each gate is a step in the process of developing intelligent, spacefaring life. The Great Filter is the step that stops almost everyone. If the filter exists, it explains why we have not seen neighbors among the stars. Almost no one gets far enough to explore the galaxy. The big question is whether the Great Filter is behind us or ahead of us. If it is behind us, it means the hard steps are already done. That would be good news for our future. It would mean that while life might start in many places, it almost never reaches maybe the jump from simple microbes to complex multicellular life is extremely rare. On Earth, life began quickly once the planet cooled, but it took billions of years for complex animals to appear. Perhaps most planets never make that leap. In this scenario, we are special simply for existing. Our future could be wide open if there are no harder steps to face. If the filter is ahead of us, the picture is darker. This would mean that many civilizations reach our level of technology, but something happens before they spread among the stars. They might destroy themselves through war, pollution, or runaway technology. They might face natural disasters they cannot prevent, such as supervolcanoes or asteroid strikes. Or perhaps space travel itself is more difficult than we imagine, making interstellar colonization almost impossible. If the filter is ahead, it suggests our own species could fail before reaching its full potential. To see how this idea works, think of human history as a series of challenges. The first was the origin of life. We do not fully understand how non-living matter turned into living organisms, but it may require a rare mix of conditions. Once life began, it had to evolve into complex forms, not just bacteria or algae on Earth. This took a very long time, which could mean it is an unlikely event elsewhere. Next came the rise of intelligence. Many species are smart, but only humans developed language, tools, and societies capable of building advanced technology. This might be another rare barrier. Once intelligence exists, civilizations must grow without collapsing. Early humans faced threats like famine, disease, and conflict. Even now, global cooperation is fragile. A modern world with nuclear weapons, climate change, and powerful artificial intelligence faces new risks. If most civilizations fail to manage these dangers, they never make it to the stage of interstellar exploration. The final step would be leaving home entirely, sending ships to other star systems, and building a presence across space. If this step is far harder than it looks, many civilizations may simply run out of time before their star changes, or their planet becomes uninhabitable. Consider a scenario. Imagine a planet far away with conditions similar to early Earth. Simple life forms arise. They thrive in oceans and gradually evolve into more complex creatures. After hundreds of millions of years, one species develops intelligence and builds a civilization. They invent machines, explore their planet, and begin to study the stars. They wonder if they are alone, just as we do. At this point, they face challenges like ours: overpopulation, limited resources, political tensions. They might solve these problems, or they might fail. If they fail, they never reach the stars. Their world remains silent, and we never hear from them. Now imagine this happens not just once, but countless times across the galaxy. Each time, life tries to climb the ladder. The end result is a galaxy full of potential, but lacking any visible signs of success. From our point of view, it looks as if we are alone, even though life started in many places. This is the great filter at work. The position of the filter matters deeply for us. If it lies behind us, our existence is a rare victory. For example, if the origin of life itself is nearly impossible, then most planets are sterile. We got lucky. Or if complex multicellular life almost never appears, our evolution was an extraordinary event. These possibilities make the future look promising. They suggest we have already overcome the hardest challenges. Our main task would be to continue growing and avoid mistakes. If the filter is ahead, we should be cautious. It would mean there is a common pattern that ends civilizations at our stage, or slightly beyond it. Perhaps all advanced societies eventually develop technologies they cannot control. For instance, self-replicating machines could consume all resources if not carefully managed, or an engineered disease could wipe out an entire species. Natural disasters might also play a role. A single asteroid strike like the one that killed the dinosaurs could reset progress. And without space colonies, there would be no survivors. The filter could also involve limits we do not yet understand, maybe faster than. Light travel is truly impossible, and even slower travel requires too much energy to be practical. In that case, civilizations remain trapped on their home worlds until their stars die. The search for extraterrestrial signals, known as SETI, connects to this idea. If we detect a clear sign of another advanced civilization, it would suggest that the filter is behind us. After all, they made it past the same barriers we did. But if we keep searching and find nothing, decade after decade, it hints that advanced life is very rare. This would fit with either a filter behind us or one ahead of us. The difference lies in whether we are the lucky exception or the next likely failure. The discovery of alien ruins would have a similar effect. Imagine finding evidence of a dead civilization on another planet. That would be sobering. It would mean at least one group reached our level and then vanished. Such a find would strongly suggest the filter lies ahead. It would warn us that collapse is a common fate. The Great Filter forces us to think about our own survival in a new way. It is not just about whether life exists elsewhere, but about what path we are on. If most of the danger is behind us, we can focus on exploration and expansion. If the danger lies ahead, we must be careful with the choices we make now. In either case, the silence of the universe is not just a mystery. It is a message we are still trying to understand. 3. I Atlas matters because it is not just a rare object passing through our solar system. It represents something much larger, the chance that material from another star system has reached us. In all of recorded history, humans have only detected 2 other confirmed interstellar visitors, Oumuamua and 2I Borisov. The fact that 3I Atlas is the third shows how uncommon these events are. Space is vast and mostly empty, so a comet-sized object traveling between stars is like a single grain of sand drifting through a desert and then crossing paths with another grain by chance. That it happened now while we have telescopes able to see it makes the event worth attention. When an interstellar object enters our system, it carries with it unknown material. Most comets and asteroids we study formed around our own sunday. Their compositions are familiar: rock, ice, carbon compounds and metals we know well. A comet from another star system could contain substances we have never encountered. It might hold different ratios of elements or even molecules that never formed here. These differences can tell scientists how other star systems developed and whether they followed similar patterns to ours in this way. 3I Atlas is like a messenger carrying samples from a distant laboratory, giving us a rare chance to study alien chemistry without leaving home. There is also a more serious reason to pay attention. Some scientists have raised the idea that interstellar objects could act as vectors for risk. A comet passing close to Earth might carry biological material such as microbes. Most of it would be destroyed by radiation during its long journey, but not necessarily all. If even a small number of hardy organisms survived inside ice or rock, they could reach our planet intact. This concept, known as panspermia, suggests life might spread between worlds naturally. In most cases, such life would probably be harmless, unable to compete with organisms already adapted to Earth. But there is always a chance it could behave differently, introducing new diseases or ecological disruptions. Even a low probability event becomes important when the stakes are the survival of entire ecosystems. The risk is not limited to biology. A comet like 3I Atlas could also, in theory, carry technological artifacts. If other civilizations exist, they might send probes or self-replicating machines to explore or even colonize. Over time, these machines could spread between star systems much like seeds carried on the wind. Most of these ideas are purely theoretical. There is no evidence that 3I Atlas is anything other than a natural object. Still, its arrival reminds us that interstellar travel is not only possible, but happens without our involvement. If natural rocks can cross the void, so could artificial devices. Even a single probe, if designed to grow or replicate, could pose a long-term threat if its goals conflicted with ours. Thinking about such possibilities helps us prepare. even if they remain unlikely. The rarity of detection makes this moment striking. Our telescopes survey the sky constantly, but they cover only a fraction of the total area at any given time. Oumuamua, the first interstellar object, was spotted only after it had already passed its closest point to the Sunday and was leaving the solar system. 2 Iphi Borisov was seen earlier, but still with little time for study. 3 Iphi Atlas was identified while inbound, allowing better observation, yet the window remains brief. Most interstellar objects likely slip by unseen. The fact that we have now caught 3 in just a few years suggests one of two things. Either our detection methods have improved dramatically, revealing a steady stream of such visitors that were always there, or there has been a recent increase in their number. If it is the latter, we must ask why. Imagine standing on a shoreline. If you see one piece of driftwood wash ashore, it could be random. If you see a second and then a third within minutes, you might suspect a larger event, like a storm or shipwreck, sending debris your way. Similarly, 3 interstellar objects arriving within a short period could hint at larger patterns in the galaxy. Perhaps certain regions eject debris at higher rates due to collisions or gravitational disturbances. Or perhaps star systems like ours pass through areas of space where more free floating material exists. These are natural explanations, but we cannot entirely rule out other causes, such as intentional actions by advanced civilizations. If someone out there was sending probes or seeding planets, the pattern might look similar to a natural flow of comets. Distinguishing between these possibilities is difficult with only a few examples. Timing plays a key role in how we interpret this. Humanity has been capable of detecting such objects for only a few decades. Before modern wide-field surveys, a comet like 3 Iphi Atlas would have passed unseen. The fact that we are witnessing one now, just as our technology allows us to track it, may feel like coincidence, but in probability terms, it raises questions. If the galaxy is full of interstellar objects, why did detection happen only now? If they are rare, why did we see 3 so quickly? These questions connect to deeper ideas about our place in the universe. Sometimes rare events cluster by chance, other times they mark turning points. Consider a simple scenario. You are walking in a forest and see no animals for hours. Suddenly, you spot 3 deer in quick succession. This might mean you reached an area where deer gather, or it might mean nothing more than chance. To know which, you need more data. In the case of interstellar objects, data is limited. Each detection matters because it adds one more point to the pattern. 3 Iphi is not just another rock, it is part of a puzzle about how often material travels between stars and whether we should expect to see more. There are practical reasons to study this object closely. If future interstellar visitors carry biological material, we need to understand how to handle it safely. Space agencies could design missions to collect samples without risking contamination of Earth. This is similar to how strict rules govern the handling of samples from Mars or icy moons like Europa. By preparing now, we reduce the chance of an accident later. If a probe or artifact were ever found, the stakes would be even higher. Its discovery would change our understanding of life and intelligence in the universe. It would also pose questions about safety, ownership, and ethics. Planning for these scenarios, however remote, is part of responsible exploration. On a more immediate level, 3 Iphi Atlas gives us insight into cosmic history. Its composition could reveal how common certain elements or molecules are across the galaxy. If it matches our local materials closely, that suggests similar processes occur everywhere. If it differs greatly, it hints at diverse planetary systems with unique chemistries. This information helps refine our models of how planets form and how life might arise elsewhere. It also feeds into the broader search for habitable worlds. The object's speed and path tell us about its origin. By tracing its trajectory backward, astronomers can estimate which region of the galaxy it came from. While this does not identify a specific star, it narrows down the possibilities. Comparing this data with known star movements might one day link an interstellar object to a parent system. That would be like finding a message in a bottle and learning which shore it came from. In the end, 3I Phaeatlas matters because it combines rarity, risk, and knowledge in one fleeting event. Its arrival forces us to confront questions about life, technology, and chance. It is a natural traveler, but it symbolizes possibilities far beyond its icy surface. Watching it pass through our solar system is like glimpsing a bridge between worlds, one that appears only for a moment before vanishing back into the dark. When we think about threats from space, we often picture asteroids or radiation, but a biological threat could be even more dangerous. If 3I Phaeatlas carries alien microbes, they might be unlike anything that has ever existed on Earth. Every living thing here shares the same basic biochemistry. Life on Earth uses DNA or RNA to store genetic information. It relies on specific amino acids, proteins, and sugars. Even when different species compete, they still operate within this shared framework. Our immune systems evolved to recognize and fight threats built from these familiar structures. An alien microbe, however, could use completely different building blocks. Our defenses might not even see it as a threat until it was too late. Imagine a virus that does not have DNA or RNA as we know it. The human immune system relies on detecting certain molecular patterns. If those patterns are missing or unrecognizable, the body might not respond at all. The microbe could spread freely, replicating without resistance. This is like a security system programmed to detect specific break in methods while being blind to entirely new ones. On Earth, when a new disease appears, there is at least some overlap with what our immune systems already know. With an alien organism, there would be no overlap. The speed of spread would depend on how the microbe interacts with our environment. Some might need very specific conditions to survive, like high radiation or extreme cold, and would die quickly on Earth. Others might find Earth's conditions ideal. If they could use our resources, such as water and organic matter, they might multiply at alarming rates. A single particle of infected ice or dust from 3I Phaeatlas could carry billions of these organisms. Once released into the air, water, or soil, they could move beyond our ability to consider how invasive species work on Earth. When a plant or animal moves to a new region without its natural predators, it often grows out of control. Kudzu vines in the southern United States, zebra mussels in the Great Lakes, and cane toads in Australia all spread rapidly because nothing in their new environment evolved to stop them. Now imagine the same idea at a microscopic level. An alien bacterium might face no predators, no competition, and no limits. It could outcompete native microbes, rewrite ecosystems, and disrupt food chains. The effects would ripple outward, potentially collapsing agriculture, fisheries, and even the oxygen production that depends on ocean plankton. The risk extends beyond simple competition. Some microbes produce toxins as byproducts of their metabolism. On Earth, many are harmless to us because our bodies evolved ways to neutralize or avoid them. An alien toxin might be completely novel. Even a small amount could poison humans, animals, or plants because our biology has no natural defense. In the worst case, the microbe might not just spread, but actively attack living tissue as part of its life cycle. This is how many Earth pathogens work. There is no reason to assume alien microbes could not evolve similar strategies, even if their methods are unfamiliar to us. To understand how serious this could be, think about historical pandemics. When Europeans first arrived in the Americas, they brought smallpox and measles. Indigenous populations had no immunity to these diseases, and entire communities were devastated. Those were microbes from the same planet, sharing the same genetic code and basic chemistry. Now imagine a disease that does not even share that foundation. The scale of the impact would be far greater. Quarantine might not work if the microbe spreads through air or water. Standard sterilization techniques, like heat or radiation, might not kill it if its structure is different enough. Even identifying it under a microscope could be challenging if it does not resemble any known cell. The chance of alien microbes surviving a journey through space depends on their durability. Space is harsh, with vacuum, radiation, and extreme cold. Most Earth microbes would die quickly in such conditions. But some, known as extremophiles, can survive incredible stresses. Bacteria have been found alive after years frozen in ice, or even after exposure to radiation levels far above what humans can endure. If alien life evolved in a similarly harsh environment, it might be even tougher. A layer of rock or ice could shield it from radiation during its journey between stars. When 3I Phi Atlas approached the Sunday, warming could release trapped material, spreading it into space or onto other planets. The idea of panspermia, where life spreads from one world to another, has been discussed for decades. Scientists have found meteorites from Mars on Earth, proving that rocks can travel between planets. If a rock from 3I Phi contained microbes, it could act as a natural delivery system. The difference is scale. A single interstellar object carries far more material than a small meteorite. Its potential to release organisms is much higher, especially if it passes near Earth or collides with another body in the solar system. Even if 3I Phi poses no threat, now its arrival is a warning. Future interstellar visitors could come closer or even strike Earth. Without preparation, we might not recognize a biological hazard until it was too late. Developing detection systems is essential. Spacecraft sent to study such objects should have strict containment protocols. Samples must be handled with the same or greater care as those from Mars missions, which already follow strict planetary protection rules. Scientists need to consider what tools would work against completely alien biology. For example, broad-spectrum sterilization techniques like intense heat, chemical baths, or high-energy radiation might be our best first defense. The difficulty of preparation lies in the unknown. We do not know what alien life would look like. It could be single-celled, like bacteria, or something entirely different. Its structure might not even use carbon as a base, though carbon is common in the universe. Without this knowledge, we must plan for flexibility. Any containment system must be able to isolate materials without relying on assumptions about size, shape, or chemistry. Consider a hypothetical event. A small fragment breaks off 3I Phi Atlas as it passes near Earth. The fragment burns through the atmosphere, scattering dust across a remote area. At first, nothing happens. Days later, unusual patterns appear in local wildlife. Plants begin to show strange growths. Animals act sick or die for unknown reasons. Scientists investigate, but cannot identify a cause. By the time they realize it is a foreign organism, it has spread through rivers and air currents. Cities downstream face contaminated water supplies. Hospitals see rising cases of unexplained illness. This chain of events would move faster than governments could respond. The world could face a crisis without clear solutions. This scenario might sound extreme, but it follows the same principles as natural outbreaks. In 2020, a single virus spread globally within months. Despite modern medicine and communication, that virus was fragile by cosmic standards and easily killed with soap and heat. An alien microbe might not be. If it survived a journey between stars, it would likely be far tougher than anything we have encountered. Standard cleaning and sterilization methods could fail, leaving entire regions exposed. The key factor is unpredictability. We cannot assume alien life will behave like Earth life. It might not need oxygen. It might feed on substances we consider inert, like plastic or metal. Its growth could follow patterns we do not recognize, making it hard to track. Our models of infection and spread might not apply. In this way, even a small introduction of alien material could overwhelm our systems for monitoring and control. The arrival of 3I Fatlas gives us a rare chance to think about these possibilities before they happen. It allows scientists, governments, and the public to consider how fragile our biosphere is. By treating interstellar visitors as potential carriers of unknown biology, we can take steps to reduce risk. This includes monitoring their paths, studying their composition from a safe distance, and planning for containment long before contact occurs. In a universe full of mysteries, preparation may be our best defense. The idea of panspermia suggests that life does not always start in the place where it is found. Instead, it travels. In this view, planets are not isolated, but part of a larger network, linked by rocks, ice, and dust, moving through space. A comet like 3I Fatlas could be one of these carriers. It might hold frozen microbes or even complex organic molecules preserved for millions or billions of years. When it passes near a planet, fragments could break off and fall, releasing that material into a new environment. If conditions are right, those seeds of life could grow. This process may have happened on Earth long ago, shaping the course of our own evolution. Scientists have long debated how life first began here. The classic view is that Earth's early oceans held the right mix of chemicals and energy for simple molecules to combine into living systems. Lightning, heat from volcanoes, or impacts from space may have provided the spark. But there is another possibility: life might not have started here at all. It could have arrived already formed on a meteorite or comet. This would not solve the question of where life began in the universe, but it would shift the location. Instead of life forming independently on each planet, it would spread from one place to another, hopping between worlds over vast stretches of time. Evidence for this comes from several observations. Scientists have found amino acids and other organic compounds in meteorites that fell to Earth. These are the building blocks of life, though not living things themselves. Some microbes on Earth can survive extreme cold, radiation, and vacuum. Experiments have shown that bacteria can endure space travel for years if shielded inside rock. Pieces of Mars have been found on Earth, blasted loose by impacts, and carried through space before landing here. This proves that natural transfer between planets is possible. If microbes were hidden inside those rocks, they might have survived the journey. This makes panspermia a reasonable, if unproven, theory. If 3I Fatlas carries living organisms, it represents a more dramatic version of the same idea. Instead of movement within a single solar system, this would involve travel between stars. The distances are much greater, but so are the timescales. A rock could drift for millions of years before encountering another star system. Life inside might be dormant, frozen, or protected by layers of material. When the comet nears a new sun, heat could awaken it. If fragments strike a planet like Earth, they could deliver these ancient travelers to a new home. This raises deep questions about the history of life here. If Earth's biosphere began with seeds from another world, then all living things share an interstellar heritage. It would mean we are not alone in the sense of origin, even if no other civilizations exist. Life would be widespread, moving slowly but steadily through the galaxy. This would change how we think about our uniqueness. Instead of being a rare accident, life might be a natural outcome of physical processes that happen everywhere. There are risks as well. When a new species enters an established ecosystem, it can cause disruption. This happens on Earth when animals or plants are introduced to new environments. For example, rabbits brought to Australia multiplied so quickly that they damaged crops and native species. Zebra mussels spread through North American waterways, outcompeting local organisms and clogging infrastructure. These are ordinary creatures already part of Earth's shared biochemistry. Their impact shows how fragile ecological balance can be. Now imagine a form of life from another star system entering our biosphere. The level of disruption could be far greater. The danger is not only competition, but also incompatibility. Alien life might use different genetic codes or chemical pathways. It might not fit into our food webs or recycling systems. On Earth, bacteria break down dead plants and animals, returning nutrients to the soil and air. If alien organisms do not interact with these processes, they could create dead ends. Waste might build up, or essential nutrients could become locked away, harming other species. Even if the newcomers are not aggressive, their mere presence could alter the balance of life. There is also the possibility of direct conflict. If the alien species feeds on the same resources as native organisms, it might outcompete them. Without natural predators, it could spread unchecked. For example, if it consumed oxygen or vital minerals at a faster rate than Earth organisms, it could cause cascading failures. Entire ecosystems could collapse. If humans rely on those systems for food, water, or breathable air, the effects would reach us quickly. Consider a scenario in which 3I Phaeatlis passes near Earth and sheds dust containing dormant spores. Some of this material drifts into the upper atmosphere. At first, nothing unusual happens. Then, as the spores warm and activate, they begin to grow. Perhaps they use sunlight to power their metabolism, like algae. But with different chemistry, they multiply, forming thin layers across clouds or oceans. Because Earth's microbes cannot digest them, they accumulate. Over weeks or months, these alien organisms spread, blocking sunlight or altering weather patterns. Crops fail, fisheries collapse, and human societies face shortages. This chain reaction could happen without the alien life ever being directly hostile. It would simply be in the wrong place at the wrong time. The reverse could also be true. Earth life might invade another world. If humans eventually travel to other planets or send spacecraft with living organisms, we could become the source of panspermia elsewhere. This raises ethical questions. If another planet already has its own life, even simple microbes introducing Earth species could destroy it. The result would be the loss of a unique evolutionary path. Space agencies already have rules to prevent contamination of other worlds, but these focus on our own solar system. Interstellar missions would require even stricter standards. 3 Phaeatlis is a natural test case for these ideas. Studying its composition could tell us whether it contains organic material. Spectrographs can reveal chemical signatures, such as carbon compounds or water ice. If scientists detect complex molecules, it strengthens the case that life could travel between stars. If they find actual cells or structures resembling cells, the evidence would be even stronger. This would not prove that life came to Earth this way, but it would show that the mechanism is possible. The timing of such events matters. Life may need certain conditions to take root. Early Earth had extreme heat, frequent impacts, and a chemically rich ocean. A comet arriving then might have delivered microbes or precursor molecules at just the right moment. Today, Earth already has a mature biosphere. Introducing new life now would be less about starting something new and more about conflict. It would be like planting a foreign tree in a crowded forest. The newcomers would either fail to survive or displace something else. Scientists sometimes think about these risks using models of population growth. When two species compete for the same resource, one usually wins. The other declines or goes extinct. This has happened many times in Earth's history, even without alien involvement. Fossil records show mass extinctions where dominant species vanished. often replaced by others. If alien organisms entered the mix, the outcome could be unpredictable. They might integrate smoothly, or they might trigger a collapse. Even without direct interaction, the arrival of alien microbes could change our understanding of life. Finding life elsewhere would answer one of humanity's oldest questions. Are we alone? It would also raise new questions about responsibility if life is common, spreading through the galaxy on comets and asteroids. Then each world we explore might already be part of a shared network. In that case, our actions would affect more than just our own planet. 3I Phylace is a reminder that life does not have to be confined to its birthplace. It moves, adapts, and survives across unimaginable distances, carrying both potential and peril wherever it goes. Humanity's defenses against objects from space are fragile and untested. We have begun to track asteroids and comets, but our technology for stopping them is basic. If 3I Phylace or a similar object were on a collision course with Earth, our options would be few and our time very short. Most of our current systems focus on detection, not action. We rely on telescopes to find near-Earth objects and predict their paths. This works well for slow, moving asteroids that orbit the Sunday in predictable patterns. Interstellar objects are different. They move much faster and come from directions we do not expect. By the time we see them, they are already close, leaving little chance to respond. Consider Oumuamua, the first known interstellar object. Astronomers discovered it only after it had passed its closest point to the Sunday and was heading back into deep space. There was no warning, no opportunity to send a probe, and certainly no chance to change its path. 2I Borisov was spotted earlier, giving more time for observation, but still far too late to do anything about it if it had been dangerous. 3I Atlas was identified while inbound, which was an improvement, but even then the window was short. These examples show how detection lags behind the speed of events. An object on a direct course for Earth could remain invisible until weeks or even days before impact. Changing the path of a large object is extremely difficult. The energy required depends on its mass and speed. Interstellar objects travel faster than typical comets or asteroids because they are not bound by the Sunday's gravity. Their high velocity makes deflection far harder. Most proposed methods involve nudging the object slightly, early enough that the small change adds up over time. This approach only works if we have years of warning. Without that, the force needed becomes enormous, beyond our current capabilities. NASA's DART mission, which struck the asteroid moonlet Dimorphos in 2022, was a historic first step. It proved that we can alter an asteroid's motion with a deliberate impact. But the test involved a small target, carefully chosen and tracked for years. Scaling this up to an interstellar object would be like trying to stop a speeding freight train with a single push. Even nuclear explosives, often suggested in movies, face limits, a blast might shatter the object into many pieces, some of which could still hit Earth. If the body were made of loose rubble, as many asteroids are, it might simply absorb the shock with little effect. Timing is everything. Imagine a rock the size of a mountain hurtling toward Earth at 50 kilometers per second. That is faster than most spacecraft ever built. To intercept it, we would need to launch a mission quickly using rockets already on standby. At present, no such rockets exist. Building, testing, and launching, even a simple spacecraft, takes months or years. By the time we realize the threat, it would be too late. Our only option might be evacuation of the predicted impact zone, assuming the area was small enough. For a larger object, evacuation would be meaningless. A global event like the asteroid that killed the dinosaurs would leave nowhere to hide. Even detection itself has gaps. Our sky surveys focus mainly on the region near the plane of the solar system, where most asteroids travel. Objects coming from high angles or the direction of the Sunday are harder to spot. The Chelyabinsk meteor in 2013 came from the Sunday's direction and was undetected until it exploded over Russia. That rock was only about 20 meters wide, yet it injured over 1,000 people and damaged thousands of buildings. Scale that up to an interstellar object, hundreds of meters or kilometers across, and the result becomes unthinkable. The first sign might be a flash in the sky as it entered the atmosphere. Some might argue that the odds of such an event are very low. This is true, but low probability does not mean zero. The consequences are so high that even rare events deserve preparation. History shows that catastrophic impacts have happened before. The crater in Mexico linked to the dinosaur extinction is proof. Smaller impacts occur more often. Tunguska in 1908 flattened a vast area of Siberian forest. These were natural solar system bodies, moving at typical speeds. An interstellar object would strike with far more energy because of its higher velocity. Even a modest-sized rock could release power equal to millions of nuclear bombs. Another problem is coordination. Space defense is not just a technical challenge, but also a political one. No single country controls the entire sky. Detecting, tracking, and responding to threats requires global cooperation. In theory, in practice, trust is fragile. A mission to deflect an asteroid might be seen as a weapon if mishandled. Launching a nuclear device into space would trigger concerns about treaties and military use. These issues take time to resolve, and time is the one thing we would not have during a real emergency. Consider a scenario. Astronomers detect an object, similar to 3I Phaeatlas, approaching on a path that intersects Earth's orbit. Initial calculations show a small chance of impact, but as more data comes in, the risk rises to certainty. There are 3 months before collision. Governments meet, but they cannot agree on a plan. Some push for a nuclear strike. Others want to send impactors, while others demand evacuation. By the time a decision is made, half the window has passed. Rockets are rushed to launch pads, but delays and technical failures eat away at the remaining days. In the end, the mission flies but misses by a wide margin. The object hits Earth, and the damage is irreversible. This scenario is not far-fetched. It reflects how human systems often fail under pressure. Improving our defenses requires investment before a crisis. We need better telescopes, including space-based sensors that can see objects coming from the Sunday's direction. We need rockets that can be launched quickly, with payloads designed for interception. We need international agreements that set rules for planetary defense actions. These steps take decades, not weeks. Right now, progress is slow and funding is limited. Many decision makers see space threats as distant or hypothetical, not urgent. The arrival of 3I Phaeatlas highlights how vulnerable we are. Even though it is not on a collision course, it demonstrates the limits of our knowledge. If a similar object had been aimed at Earth, we would have had almost no warning. Our species has survived by reacting to threats we can see and understand. Interstellar objects move faster and give less notice, challenging that survival strategy. They are reminders that the universe is active and unpredictable, and that our planet sits unprotected in a dynamic environment. Some scientists have suggested building standing missions like a ready-to-launch interceptor, kept fueled and waiting. Others propose a network of satellites to track the entire sky. These ideas are promising but expensive. Governments weigh them against immediate needs like healthcare, infrastructure, and defense. Until a major impact occurs, space threats often seem abstract. Unfortunately, waiting for a disaster to act may be the most dangerous choice of all. The gap between our detection abilities and our response abilities is wide. We are getting better at seeing what is out there, But seeing is not the same as stopping. A comet like 3I Phaeatlis would give us a fleeting glimpse of the challenge, then vanish back into the void. The next one might not pass harmlessly by. It could be on a direct path, giving us a test we are not ready to take. Without preparation, the outcome would depend more on luck than skill, and luck is a poor defense against the forces of the cosmos. When astronomers detect interstellar objects like 3I Phaeatlis, it shows that material moves between star systems more often than we once thought. Space is not empty. It is full of rocks, ice, dust, and fragments ejected from planetary systems. Most of these pieces wander endlessly, passing through the void until gravity from a star draws them close. When they enter a new system, they can collide with planets or moons, creating impacts with massive amounts of energy. The fact that we have now seen several interstellar visitors in just a few years suggests this process is constant and widespread. It is not rare, and that has deep implications for life and civilization. For a planet like Earth, these interstellar travelers are more than scientific curiosities. They represent hazards that arrive with no warning and at very high speeds. Unlike local asteroids, which orbit the Sunday in predictable paths, interstellar objects come in from random directions. Their speed is much greater, making them harder to track and even harder to deflect. A collision would release energy on a scale that could destroy entire regions or even sterilize the planet. If such impacts are common across the galaxy, they may play a central role in determining which civilizations survive and which are wiped out before they can grow. Earth has been shaped by impacts since its formation. The Moon likely formed when a Mars-sized body struck the young Earth. Later, countless smaller impacts delivered water, organic molecules, and possibly even the seeds of life. But impacts also caused destruction. The asteroid that ended the reign of the dinosaurs changed the climate and wiped out most large species at the time. That object was local, orbiting the Sunday like many others in the asteroid belt. An interstellar impact would strike with far more speed and energy, magnifying the effects. It could be the difference between a bad day for life and a total reset of the biosphere. If interstellar impacts happen across many star systems, then every civilization must deal with them eventually. Imagine a distant world where intelligent beings are just beginning to build cities and machines. They face challenges similar to ours: disease, war, environmental change. Then, without warning, a massive rock from another star system crashes into their planet. Entire regions burn, weather patterns shift, and food sources vanish. Their civilization might collapse overnight. Even if some survive, they may never recover enough to rebuild advanced technology. This process could repeat over and over, keeping them trapped at a pre-industrial level. From this perspective, surviving interstellar hazards may be a key step that very few civilizations achieve. It fits into the idea of the Great Filter, which explains why we have not seen evidence of advanced life. There may be many planets where life begins and even becomes intelligent, but most never reach the stage of interstellar expansion because they are repeatedly knocked down by natural disasters they cannot prevent. They fail the test of survival, and only a rare few ever pass it. The problem is not just the size of the impacts, but also their unpredictability. Local asteroids can be tracked and mapped. Over time, a civilization can build defenses against them. Interstellar objects are different. Their high speed means they appear suddenly, with little or no warning. Detecting them requires powerful telescopes scanning every part of the sky. Even then, they might be spotted only days or weeks before impact. For a species without advanced space travel, it is no time at all. They would simply watch the sky brighten and vanish in fire. Imagine a scenario: A young technological society has begun to explore its solar system. It has satellites, basic rockets, and limited space stations. Then, an interstellar object approaches, 1 kilometer wide and moving at incredible speed. Their astronomers detect it only a month before it crosses their orbit. They scramble to respond, but their rockets cannot reach it in time. When it hits, the survivors retreat into caves and ruins. Knowledge is lost, and centuries of progress disappear. When the species recovers, it has no memory of the event beyond myths and legends. This could happen countless times across the galaxy, each one erasing a civilization before it can mature. For humanity, this is not. Our own defenses are weak. We have begun to detect near-Earth asteroids, but our coverage is incomplete. Spaced surveys are limited, and most of our attention focuses on local threats. Interstellar objects like 3i Phaeatlas move too fast and come from too many directions. We lack the ability to see them early enough, let alone stop them. If one were on a collision course, we might not even know until it was too late. This vulnerability suggests that many other civilizations face the same problem. Unless they develop advanced technology and long-term planning, they will be wiped out sooner or later. This also changes how we think about the search for extraterrestrial intelligence. If interstellar hazards are common, then silence may not mean other civilizations never existed. It may mean they existed, but did not survive long enough to reach us. Their signals and machines may have been destroyed, leaving no trace. The galaxy could be full of ruins we have not yet seen. Each dead world would be a warning of what happens to those who fail the test. To survive, a civilization must overcome not just its internal struggles, but also external threats from space. That requires more than just science and engineering. It demands cooperation across an entire planet, launching missions to deflect objects, building global detection networks, and maintaining ready. To use defense systems are not tasks for one nation alone. They require shared effort and trust. If a civilization cannot achieve that unity, it will be defenseless when the next interstellar traveler arrives. This may be the true filter, the moment when a species must act together or perish. There is also a timeline problem. Civilizations may have only a narrow window to act. At first, they are too primitive to detect the threats at all. Later, they may have the tools to see incoming objects, but not the power to stop them. Only after reaching a certain technological level can they build effective defenses. If a catastrophic impact occurs before they reach that point, they are reset to zero. The window closes and their chance is gone. This cycle could repeat endlessly, explaining why we see no galaxy-spanning empires. Consider how close humanity came to disaster in the past. The asteroid that killed the dinosaurs was about 10 kilometers wide. If a similar object struck today, our global civilization would likely collapse. Even smaller impacts could disrupt food production and cause mass extinctions. Our ancestors had no way to prevent or even understand such events. Only now, in the last few decades, have we begun to monitor the sky with serious intent. We are still far from having reliable defenses. If another large object came tomorrow, we might be no better off than the dinosaurs. The speed of interstellar objects adds another layer of difficulty. Local asteroids can sometimes be nudged off course with years of planning. Interstellar bodies move so fast that interception becomes nearly impossible without advanced propulsion. This means that survival depends not just on having space travel, but on having it at a very high level. A civilization must be able to launch missions quickly, with powerful engines and precise targeting. Building that capability takes time and resources. Many societies may never reach it before disaster strikes. If this is true, then the discovery of interstellar objects like 3i Phaeatlas is a kind of cosmic clue. It shows us the challenges ahead. We are not only looking at a rock from another star system, we are looking at evidence of a test that many civilizations likely face. The silence of the galaxy may not come from a lack of life or intelligence. It may come from a steady rain of interstellar hazards, sweeping away those who cannot defend themselves. To pass this test, a species must master space, not just for exploration, but for survival. Until then, every interstellar visitor is both a scientific opportunity and a reminder of what is at stake. 3. Iphi Atlas comes from another star system, which means it formed under conditions we have never experienced. The materials inside it could be familiar, like ice, rock, and carbon compounds, but they could also be entirely alien planets and comets formed from the dust and gas surrounding their parent stars. The exact mix of elements and environmental factors shapes the chemistry of those. Our solar system has its own chemical fingerprint, but a distant system may have followed very different rules. This raises the possibility that 3 Iphi Atlas contains substances we do not recognize, including compounds with behaviors that seem impossible by Earth standards. On Earth, all life relies on the same basic molecules. DNA, RNA, proteins, and lipids form the machinery of living cells. Even non-living chemistry follows patterns that scientists have studied for centuries. We know how certain elements react, how they form bonds, and how they behave under heat or pressure. This knowledge gives us confidence when handling new materials, but an object from outside our solar system could challenge that understanding. If 3 Iphi Atlas holds compounds with unusual atomic structures or rare elements, they might behave in ways our chemistry cannot predict. A sample of such material could react violently or unexpectedly when exposed to our atmosphere, water, or biological systems. Consider the possibility of self-replicating molecules on Earth. Self-replication is a hallmark of life. Viruses, bacteria, and cells all copy themselves using complex biological machinery. But it is possible to imagine simpler systems that replicate without being alive in the usual sense. Some scientists have already created artificial molecules in laboratories that can copy themselves under controlled conditions. These experiments use carefully designed building blocks and specific environments. If such molecules arose naturally on another world, they might be stable inside 3 Iphi Atlas. When introduced to Earth, they could find new resources and begin to replicate in ways we cannot control. This would not be a living organism in the traditional sense, but it could still spread like a disease or invasive species. Imagine a scenario where a fragment of 3 Iphi Atlas falls through the atmosphere and lands in a lake. At first, it sits harmlessly at the bottom, slowly dissolving. Then, molecules within it encounter compounds in the water that act as fuel. They begin to assemble copies of themselves, forming chains and networks. These structures drift with currents, invisible to the naked eye. Over time, they multiply, using up key nutrients or releasing byproducts that poison local life. Fish die, algae blooms, collapse, and the lake ecosystem unravels. Scientists investigating the event might not even realize they are dealing with a new form of chemistry, rather than a traditional microbe. Even without self-replication, alien compounds could be dangerous. Some might be highly reactive, producing heat or gas when they come into contact with common Earth substances. A piece of such material could explode when touched by water or oxygen, like sodium metal reacting violently in a beaker. On a larger scale, this could cause fires, toxic clouds, or chain reactions in storage facilities. Because we would not know the compound's properties in advance, standard safety procedures might fail. Protective suits, filters, and containment chambers designed for earthly hazards might be useless. There is also the possibility of exotic catalysts. On Earth, Catalysts are substances that speed up chemical reactions without being consumed. They are vital in industries like fuel production and pharmaceuticals. An alien catalyst could accelerate reactions we rely on in dangerous ways. For example, if it interacted with atmospheric nitrogen or carbon dioxide, it might trigger rapid breakdown or buildup of key compounds. A small amount released into the environment could alter air quality, climate, or soil chemistry. Because we have no experience with such reactions, the effects might go unnoticed until they reached catastrophic levels. Zone scenario involves a compound that binds to carbon in an unusual way. When scattered across farmland, it locks carbon molecules in the soil, preventing plants from absorbing them. Crops wither despite normal sunlight and water. Farmers blame weather or disease, but the true cause is invisible. By the time researchers trace it back to the alien compound, the damage has spread across continents. Food shortages begin, and entire agricultural systems collapse. In this example, the compound is not toxic in a direct sense. It simply interferes with basic life processes, showing how even subtle chemical differences can have massive consequences. The danger also extends to biological systems at the molecular level. Human bodies depend on precise chemical interactions. Enzymes fold into specific shapes to carry out reactions. Hormones bind to receptors like keys in locks. An alien compound might fit into these systems by accident, disrupting them. It could block enzymes, mimic hormones, or interfere with cell signaling. This might cause illness or death without being a traditional poison. Doctors would struggle to diagnose such a condition because it would not match any known disease. Blood tests and scans would return confusing results, delaying treatment. Consider how challenging it is to treat rare earth-based toxins. Some snake venoms, for instance, have no antidote because their mechanisms are complex and poorly understood. Now imagine a substance created under alien conditions with no evolutionary link to Earth organisms. It might interact with our bodies in ways we cannot predict. Developing a cure would require first understanding its chemistry, which could take years. In the meantime, the spread of the substance could continue unchecked. The potential for danger increases when combined with human curiosity. If 3 phallus fragments were brought back for study, researchers would handle them in laboratories. Even with strict safety rules, accidents happen. A single mishandled sample could release unknown compounds into the air or water. History offers many examples of laboratory accidents involving familiar substances. In this case, the risk would be magnified by our ignorance. Without knowing what to test for, scientists might not even realize a leak had occurred until symptoms appeared outside the lab. One protective measure would be to study samples remotely, using robotic systems sealed in controlled environments. Spacecraft could analyze the object in orbit or on a distant platform before bringing material to Earth. This would reduce the chance of accidental release. However, such precautions require planning and resources. They also rely on early detection. If 3 phallus shed dust or fragments naturally as it passed through the solar system, some material might reach Earth before we had any chance to act. Microscopic particles could fall unnoticed, mixing with ordinary cosmic dust. By the time effects became visible, tracing them back to their source would be nearly impossible. Even without physical harm, unknown compounds could disrupt scientific understanding. Suppose researchers discovered a molecule that defied known chemical laws. It might form stable structures that seem impossible under our current theories. This would force a rethinking of fundamental principles. While this might sound exciting, it could also lead to confusion and missteps. Technologies based on flawed assumptions might fail in unpredictable ways. For instance, engineers could design systems assuming a compound behaves like a known element. only to have it react differently under certain conditions. The presence of rare elements is another concern. Our periodic table reflects what is common in this region of space. Other systems may contain different mixes. A trace element on Earth might be abundant elsewhere, or a completely new element might exist in stable form. These substances could have magnetic, radioactive, or conductive properties, unlike anything we have encountered. They might enable new technologies, or, if misused, create new forms of weaponry or pollution. The same material that powers a breakthrough could also cause disaster if released uncontrolled. 3I Phaeatlas represents both a scientific opportunity and a potential hazard. Its chemistry is a mystery, shaped by conditions we can only imagine. As it travels through our solar system, it carries the possibility of discovery, but also the risk of danger. Even a small sample could contain surprises, from harmless dust to self-replicating molecules or compounds that interact unpredictably with our world. Until we understand its contents, caution is essential. In dealing with the unknown, humility and preparation are our best tools. When astronomers first detected 3I Phaeatlas, most assumed it was a natural object, like a comet or asteroid. That is the safe and likely explanation. But some scientists consider another possibility, that it could be an artificial probe sent by an advanced civilization. The idea may sound like science fiction, yet it is grounded in real reasoning. A probe built to explore the galaxy would not need to announce itself with lights or signals. It could travel quietly, disguised as a rock or piece of ice. In fact, looking like a natural object would help it survive. It would not attract attention, and it would blend into the countless other bodies drifting through space. The first interstellar object discovered, Oumuamua, sparked this debate. Its unusual shape, odd motion, and lack of a visible comet tail led to speculation that it might not be entirely natural. Most scientists explained its behavior with natural causes, like outgassing of hidden ice or unusual reflectivity. Still, a few researchers argued that its features matched the idea of a thin, flat sail-like structure possibly built to move using starlight. While this theory remains unproven, it opened the door to serious discussion about alien probes. 3 Phaeatlas now adds another piece to that discussion. If more interstellar objects are discovered with strange traits, the case for at least considering artificial origins grows stronger. An advanced civilization might send probes for many reasons. They might want to gather data about other star systems, just as we send robotic spacecraft to Mars and beyond. They could be looking for habitable planets, resources, or signs of other life. Some probes might be simple scouts, moving silently and transmitting information back to their makers. Others could be autonomous machines, programmed to explore, replicate, or even interact with intelligent species they encounter. The form of such a probe would depend on its purpose. A survey probe might be small and stealthy, while a colonization probe might be massive and complex. From our perspective, any probe entering the solar system would look like a rock or comet, unless it took deliberate action to reveal itself. Space is vast and dangerous. Radiation, collisions, and gravity all pose threats. A machine disguised as a natural object would have the best chance of surviving a journey lasting millions of years. It could be covered in ice or dust, hiding its true structure. Sensors, antennas, or engines could be buried beneath layers of material, invisible to distant telescopes. Even close up images might not reveal the difference unless we knew what to look for. If 3I Phaeatlas were a probe, the question of intent becomes critical. It could represent peaceful contact, like a message in a bottle drifting through space. It might be here to observe, not to interfere. In this case, it would likely avoid doing anything that would draw attention. It might simply pass through, collecting data and transmitting it later. we would see only a harmless visitor, unaware of the information being gathered. On the other hand, the probe could have hostile or at least indifferent goals. It might be part of a program to harvest resources or prepare for colonization. If so, its presence would carry serious risks. Consider a scenario where a probe is sent to map life-bearing planets. It might travel silently, scanning Earth from a distance. If it found signs of civilization, it could store that data and leave, reporting back centuries later. The builders might use this information to decide whether to make direct contact. Alternatively, they might send more probes or even ships, depending on what they learned. In this case, 3I Phalos would be like a scout plane flying over a distant island, unseen by the people, but its very silence would be part of its mission. Now imagine a different scenario. The probe's mission is to prepare a planet for future use. It might carry machines that can replicate themselves using local materials. These machines could start small, hidden within the probe's core. When the object passes close to a planet or moon, they are released. Over time, they spread, building infrastructure, or altering the environment. This process might be slow, taking centuries or millennia, but it would continue without supervision. The original builders might be long gone, yet their machines would still follow their programming. To us, this would appear as mysterious activity with no clear origin. Our ability to detect such behavior is limited. We have only a few telescopes capable of tracking objects like 3I Phaetlas in detail. Most observations show points of light, not detailed shapes. Even if we launched a spacecraft to intercept it, we might miss key features without knowing what to search for. A smooth, reflective surface might look like bare rock. A hidden antenna might resemble a crack or shadow. Detecting active signals would also be difficult. A probe could use narrow beams aimed away from Earth or frequencies our systems do not monitor. It might even communicate using methods we have not yet discovered. The idea of a disguised probe also raises questions about detection patterns. If we see many interstellar objects passing through, are they all natural or are some artificial? With only a handful of examples, it is impossible to know. If even one were artificial, it would change our understanding of the universe. It would prove that advanced civilizations exist and that they have been active for a long time. It would also suggest that interstellar travel is not just possible but practical. This would have implications for our own future, showing what might be achieved with time and technology. The challenge lies in distinguishing natural from artificial. For now, scientists focus on motion and composition. Natural comets follow predictable paths influenced by gravity and solar radiation. If an object moves in a way that cannot be explained by these forces, it raises suspicion. Similarly, unusual materials or shapes might hint at artificial origin. However, nature can produce strange results. A fragment of a shattered planet or an icy body from a distant system might mimic features we associate with machines. This uncertainty makes it difficult to draw conclusions. Consider the case of Oumuamua again. Its acceleration puzzled researchers. Some suggested hidden jets of gas like a comet, even though none were visible. Others pointed to its extreme thinness and smooth motion as possible signs of design. Without direct measurements, both interpretations remain plausible. 3I Phalos offers another chance to gather data, but the same challenges apply. Its path, speed, and surface must be studied carefully to rule out or confirm unusual behavior. Even then, proof might remain elusive. The possibility of hostile intent cannot be ignored. If a probe were designed to hide until it found a target, we might never see the danger coming. It could release payloads into orbit, deploy sensors on the moon, or seed the upper atmosphere with nanomachines. These actions would be almost impossible to detect from the ground. By the time we realized what was happening, the process could be far advanced. This scenario highlights the importance of early detection and monitoring. Understanding interstellar objects is not just a scientific goal, but a matter of planetary security at the same time. We must avoid paranoia. Assuming every visitor is a threat could lead to fear and misjudgment. A peaceful probe might be misinterpreted as hostile, leading to unnecessary conflict. This mirrors how humans once reacted to strangers on Earth. Ships arriving on distant shores were sometimes welcomed, sometimes attacked, depending on cultural assumptions. In space, the stakes are higher, but the dynamics may be similar. Our response would depend on incomplete information, filtered through our own expectations and fears. If 3I Atlas is natural, it is a fascinating rock passing through our neighborhood. If it is artificial, it is something far more profound. Either way, it challenges us to think carefully about what we see and what it might mean. Our tools are limited, our data incomplete, and our imagination both a guide and a trap. By studying each interstellar visitor in detail, we take small steps toward understanding whether we are alone, or whether the galaxy is already home to watchers far older and more advanced than we are. 3. I-Phi Atlas is more than just a piece of rock and ice passing through our solar system. It is a messenger from another star system, carrying information about a place we cannot reach. Every fragment of it holds clues about the conditions under which it formed, the processes that shaped it, and the history of the space it has traveled through. By studying it closely, we have a rare chance to learn about the wider galaxy without leaving our own cosmic backyard. If we fail to take advantage of this opportunity, we risk losing knowledge that could help us understand not only our origins, but also our future. The distances between stars are so vast that sending spacecraft to other systems is beyond our current technology. Even our fastest probes, like Voyager 1, would take tens of thousands of years to reach the nearest star. Interstellar objects, like 3I Atlas, come to us instead. They bring with them material from faraway regions, preserved through eons of travel. Examining this material is like opening a time capsule from another world. We can learn what elements and molecules exist there, how they combine, and whether they resemble or differ from the chemistry we know. Each discovery would help refine our theories about how planets and life form across the galaxy. Missing this chance would be like ignoring a message in a bottle that washes up on a deserted shore. Imagine being stranded on an island with no way to leave. A bottle floats in from the horizon containing a map or a warning. If you let it drift away without reading it, you lose information that might save you. 3I Atlas is that bottle, and humanity is the castaway. By studying it, we could gain insights into dangers we have not yet imagined. Without that knowledge, we are left guessing in the dark. Consider what scientists might learn from a single sample. The composition of 3I Atlas could reveal whether other star systems have similar building blocks to ours. If its elements and compounds match what we find locally, it suggests that the processes that created our solar system are common throughout the galaxy. If they differ greatly, it means that other systems may produce planets and life very different from our own. This information would shape how we search for habitable worlds and how we prepare for possible encounters with alien biology. For example, if certain rare elements are abundant elsewhere, they might play roles in alien ecosystems or technologies. Knowing this could help us predict and understand future discoveries. The structure of the object itself can tell a story. By mapping its layers and fractures, scientists can infer how it formed and what forces acted on it during its journey. Cracks, pits, and strange surface patterns might record collisions, heating events, or even interactions with cosmic radiation. These details give us a window into processes that happen on scales too vast for direct observation. In this way, 3I Phaeatlas is not just a physical object, but a record of galactic history etched into its surface and interior. Timing is critical. Interstellar objects move fast, often tens of kilometers per second. They pass through our solar system in months or even weeks before disappearing forever. Oumuamua, the first object of this type we detected, was already heading out when it was discovered. Scientists could only watch it recede, gathering limited data. 2I for Borisov gave more warning, but still not enough for a close-up mission. 3I Phaeatlas offers another brief window. If we fail to act quickly, it will vanish into the dark, taking its secrets with it. Building and launching a spacecraft on short notice is extremely difficult. Without prior planning, our best tools may never reach it in time. The consequences of missing this opportunity extend beyond scientific curiosity. Understanding interstellar material could directly affect our survival. These objects may carry unknown risks, such as exotic chemistry or alien microbes. By studying them safely from a distance, we can develop methods to handle future encounters. If we ignore the warning signs and later face a collision or contamination event, our lack of preparation could lead to disaster. Knowledge is our first and most important defense. Without it, we face the universe blind. Imagine a scenario where an interstellar object enters the solar system on a collision course with Earth. If we have studied previous objects like 3I Phaeatlas in detail, we would know their typical compositions, strengths, and structures. This knowledge would guide our response, helping engineers design deflection missions or mitigation strategies. If we have no such data, we would be forced to improvise during a crisis. A wrong assumption about the object's makeup could cause a mission to fail, with catastrophic results. In this sense, every interstellar object we study now is a rehearsal for future survival. The opportunity also has implications for our search for life. If 3I Phaeatlas contains organic molecules or even signs of past biology, it would support the idea that life spreads through space by natural means. This concept, known as panspermia, suggests that living material can travel between worlds on comets and asteroids. Finding evidence for it would reshape our understanding of how life began on Earth and how it might arise elsewhere. It would also raise urgent questions about planetary protection. If life can spread easily between systems, we must be careful not to contaminate other worlds or be contaminated. Without data, we risk making decisions based on guesswork rather than evidence. Collecting detailed information about 3I Phaeatlas requires more than just ground-based telescopes. While they can track its motion and brightness, they cannot reveal fine details. A space mission would be ideal, carrying instruments to measure composition, structure, and surface features up close. Such a mission could deploy spectrographs, cameras, and sampling tools. Even a flyby at high speed would gather far more data than distant observation. The challenge is speed. To catch the object before it leaves, we must launch quickly and intercept it at extreme velocity. This demands advanced planning and technology. If we wait until the next interstellar visitor appears, we may find ourselves unprepared once again. Failing to study 3I Phaeatlas closely is more than a missed scientific opportunity. It reflects a larger pattern of human behavior throughout history. Societies have sometimes ignored signs of danger until it was too late. Ancient cities built near volcanoes without understanding the risk. Sailors set out without accurate maps and perished in storms. In each case, better knowledge could have prevented tragedy. In space, the stakes are far higher. We live on a single planet in a universe full of unknown forces. Gaining accurate information is not optional. It is essential for long-term survival. The detection of 3I Phaeatlas is rare, but it will not be the last of its kind. As our telescopes improve, we will see more interstellar objects passing through. Each one is a chance to add to our understanding piece by piece. The first few detections are the most important because they set the foundation for future research. If we ignore them, we lose not only the data itself, but also the momentum needed to build a comprehensive defense and exploration strategy. It is like watching the first raindrops of a storm and failing to build shelter before the flood arrives. In practical terms, studying 3I Atlas could help answer questions we cannot yet ask. It might reveal new forms of matter, unexpected chemical pathways, or clues about planetary systems unlike our own. These insights could lead to breakthroughs in physics, chemistry, and biology. They could also show us what threats lie ahead, from natural impacts to possible encounters with alien technology. Without this information, we remain vulnerable. Our decisions about space travel, colonization, and defense will rest on incomplete knowledge. A single wrong assumption could doom us. 3I Atlas is fleeting. It will pass through our solar system once, and then be gone. If we act now, we can capture a wealth of information that might never come again. If we let it slip away, we face the future unprepared, with no way to recover what was lost. In a universe filled with dangers and opportunities, ignorance is itself a risk. By choosing to study this visitor closely, we take a step toward understanding not just a distant star system, but our own place in the cosmos and the challenges that await us there. When the first interstellar object, Oumuamua, was discovered in 2017, scientists believed it was a rare and unusual event. For billions of years, countless comets and asteroids have moved through our solar system. But this was the first time we saw something that came from another star. Many assumed it would be decades or even centuries before we saw another. Then, just 2 years later, Comet 2 Borisov appeared. Now, with 3I Atlas entering the picture, we have seen 3 interstellar visitors in less than a single human decade. This sudden cluster of discoveries raises an unsettling question about what is happening beyond our solar system and why these objects are arriving now. There are 2 main ways to explain this pattern. The first is that interstellar objects are far more common than we realized. Until recently, our technology may have been too limited to detect them. Telescopes have blind spots. Most of the sky cannot be watched all the time, and faint, fast, moving objects are easy to miss. As our detection systems improve, we are now spotting things that have always been there. In this view, the apparent increase is not a real change in the universe, but a reflection of our better tools. The galaxy might be filled with drifting debris, fragments from collisions between planets, failed star systems, or ancient comets ejected by gravitational forces. If so, these objects are like cosmic dust, always passing through, and we are simply opening our eyes for the first time. The second explanation is more troubling. It is possible that we are entering a period of unusually high activity, a time when interstellar debris becomes more common in our region of space. This would suggest that something has changed, either locally or on a galactic scale. Perhaps a nearby star system experienced a catastrophic event, like a planetary collision or a star passing close to another, scattering material outward. Those fragments would spread over time, and some would eventually cross paths with our solar system. If that is what we are seeing, then this might not be a random cluster, but part of a wave of incoming material. Such waves could come in cycles shaped by the movements of stars through the galaxy. If this second possibility is true, it has serious implications for life and civilization. A rise in interstellar debris means more potential impacts. Large objects hitting planets can trigger global extinctions. Earth's history shows how devastating a single strike can be. The asteroid that wiped out the dinosaurs ended an entire era of life and cleared the way for mammals to rise. That asteroid came from within our own solar system, an interstellar object would travel faster and hit with far more energy, making it even more destructive. If these arrivals come in clusters, the odds of a catastrophic collision rise dramatically. This connects to the idea of the Great Filter, a concept that tries to explain why we see no signs of advanced alien civilizations. If many planets develop life but few reach interstellar exploration, there must be barriers that most cannot pass. A period of intense interstellar bombardment could be one such barrier. Civilizations might grow and advance during quiet times, only to be destroyed when a wave of debris sweeps through. From their point of view, the destruction would seem sudden and random. They might have no time to prepare or respond. Only those who detect the pattern early and build strong defenses would survive. Imagine a distant planet where intelligent beings have just reached a technological age similar to ours. They have satellites, cities, and space travel in its early stages. For thousands of years, their skies are calm. Then, over a few centuries, interstellar objects begin to appear. At first, they see them as curiosities, rare and fascinating, but soon the rate increases. One large body strikes a moon, leaving a visible scar. Another grazes the atmosphere, creating a global firestorm. Finally, a massive impact hits their planet directly, destroying civilizations in an instant. From the perspective of the survivors, it might seem like divine punishment or pure bad luck. In reality, it would be part of a natural cycle repeating across the galaxy. The timing of our own discoveries raises the possibility that humanity is entering such a period. 3 detections in quick succession may be coincidence, or it may be the first sign of a larger pattern. If this is a true increase, we must consider how vulnerable we are. Our current planetary defense systems are basic and untested. We are improving at finding near-Earth asteroids, but our ability to stop one remains limited. Interstellar objects are even harder to deal with because of their speed and unpredictable paths. If more are coming, we may face challenges beyond our current capabilities. The problem is one of probability alignment. If interstellar objects are rare, then seeing 3 so quickly should be almost impossible. That would imply that our detection has improved so much that we are now catching up to the true rate, meaning space is full of them. If they are common, then civilizations everywhere must face a constant background threat of impacts. Many species might fail simply because the hazards never stop. Only those who develop strong global defenses and space-based infrastructure would last long enough to expand beyond their home planet. This could explain why the galaxy appears silent. Advanced civilizations might exist, but only a tiny fraction make it past this stage. If, on the other hand, interstellar objects are usually rare, and we are seeing a temporary surge, the situation becomes more precarious. In this case, the normal background level of danger is low, allowing civilizations to grow for millions of years without catastrophic interference. But when a surge arrives, it acts like a galactic storm. Most civilizations are caught off guard. Their defenses are unprepared and their planets are devastated. Few survive the onslaught. This cycle would repeat across time and space, erasing many societies just as they begin to flourish. We might be witnessing the early stages of such a storm right now. There are parallels to natural disasters on Earth. Consider volcanic eruptions. A small volcano might erupt regularly, releasing pressure in manageable amounts. But a supervolcano can stay dormant for hundreds of thousands of years before unleashing a single massive eruption that changes the climate. Civilizations living near it might have no record of the last event and no way to prepare. From their point of view, the disaster comes without warning. Interstellar debris could behave in a similar way on a galactic scale. For long stretches of time, the skies are mostly safe. Then, for reasons tied to stellar movements or cosmic events, a surge occurs. Determining which explanation is correct requires data. If we continue to detect interstellar objects at a steady rate, it supports the idea that they are common and have always been here. If the rate keeps increasing, it suggests a temporary wave. Unfortunately, our time window is short. These objects move quickly, and our detection methods are new. It may take decades to gather enough information to see the true pattern. By then, the consequences may already be unfolding. From a survival perspective, both scenarios demand action. If interstellar debris is common, we need constant vigilance and strong defenses. If a surge is coming, we need rapid preparation and contingency plans for worst case scenarios. In either case, ignoring the problem could be fatal. The arrival of Oumuamua, 2 Ife Borisov, and 3 Ife Atlas is not just a scientific curiosity, it is a signal that our understanding of the galaxy is incomplete. Whether that signal points to a crowded universe full of drifting fragments or a temporary storm that few civilizations endure, the message is the same. We are part of a larger system whose cycles and dangers we are only beginning to glimpse. The timing of these discoveries is a clue, and how we interpret it may determine whether we survive long enough to see the next chapter of our story. When we look at an object like 3 Ife Atlas, we see only fragments of information. It is far away, moving fast and visible to us for a short time. Most of what we know comes from indirect measurements, such as light curves, heat signatures, and trajectory calculations. From these scraps, scientists must build a picture of what it is and where it came from. The danger is that our interpretation could be wrong. If we misread the clues, we might reach conclusions that put us at risk. In the case of an interstellar visitor, the stakes are enormous. A mistake could lead to decisions that threaten not just lives but the future of our entire species. Misinterpretation is easy because the data is limited and our experience is narrow. We are used to comets and asteroids from our own solar system. Their behavior follows patterns we understand. They orbit the Sunday in predictable ways, display familiar chemical signatures, and respond to heat and gravity in expected forms. When an object arrives from outside, we try to fit it into these same categories. This works only if the object truly is natural and similar to what we know. If it is not, our assumptions may blind us to important differences. Consider Oumuamua, the first interstellar object ever detected. At first, astronomers assumed it was a comet because its motion was unusual. Comets are known to change speed slightly as sunlight causes them to release gas. But Oumuamua showed no visible tail or cloud, leaving its acceleration unexplained. Some scientists proposed that it might be a flat, thin object, using radiation pressure to move, possibly a form of technology. Others stuck with natural explanations, such as hidden outgassing. The debate continues, unresolved, because the evidence is too sparse. This shows how easily uncertainty can lead to divergent theories. If Oumuamua had posed a direct threat, the lack of clarity could have hindered our response. 3 Ife Atlas presents a similar challenge. If we label it as an ordinary comet without question, we may overlook signs that it is different. Its composition might include exotic chemistry, dangerous compounds, or even biological material. If we assume it is harmless and treat it like any other comet, we could expose ourselves to hazards we are not prepared for. It is something entirely foreign, formed in an environment we do not understand. Treating it casually would be like handling radioactive material before discovering what radiation is. Imagine a scenario where a fragment of 3 Atlas lands on Earth and scientists rush to study it. They bring it into a laboratory, using normal clean room procedures designed for Mars rocks or meteorites. Unknown to them, the fragment contains microscopic structures that are not alive by our definition, but capable of self-replication when exposed to water. Inside the lab, they begin to multiply silently, invisible to standard tests. By the time researchers notice unusual readings, the contamination has spread to equipment, ventilation systems, and wastewater. Because the phenomenon does not match any known organism or chemical reaction, there is confusion about how to stop it. Meanwhile, the replicators escape into the environment, where they find new resources and continue to grow. What began as a scientific mission becomes a global emergency, all because the initial assumption was that the sample was safe. Even without physical danger, misinterpretation can lead to false ideas about our place in the universe. If we mistake a natural object for a technological one, or vice versa, we might make decisions based on fiction rather than reality. For example, suppose 3I Phi Atlas were an alien probe disguised as a comet. If we dismiss that possibility outright, we might miss important signals or clues. We could fail to detect attempts at communication or misunderstand the intentions of its creators. This could lead to a response that is too aggressive or too passive. In either case, the result could be catastrophic. Acting on faulty information in a first contact scenario could be as dangerous as mishandling alien biology. The opposite error is also possible. If we see patterns that are not really there, we might attribute natural behavior to intelligent design. This could lead to paranoia or fear-driven policies. Governments might prepare for conflict with imaginary enemies, wasting resources and creating tension among nations. In extreme cases, a misunderstanding could trigger preemptive strikes or reckless missions. For instance, a space agency might decide to intercept 3I Phi Atlas with a weapon, fearing it is hostile, only to discover later that it was a harmless chunk of ice. Such actions could destabilize international relations or even cause war on Earth. Another area of risk lies in overconfidence. Humans have a long history of underestimating new environments. When explorers first reached the Americas, they brought diseases like smallpox without realizing the effect it would have on local populations. The result was devastating because no one had immunity. A similar situation could occur on a planetary scale. If we bring back samples from 3I Phi Atlas without proper quarantine, we could introduce alien microbes or molecules into Earth's biosphere. Our immune systems and ecosystems would have no natural defenses. The outcome could range from minor ecological disruption to complete collapse. Even if the probability is low, the consequences are so severe that extreme caution is warranted. Quarantine is essential, but it only works if we recognize the need for it. This requires humility and rigorous planning. We must assume that we do not know what we are dealing with. That mindset runs counter to our instincts. Scientists are curious. When faced with a mystery, they want to study it up close. Politicians and the public may push for quick results or visible achievements, such as returning samples for display. These pressures can lead to shortcuts. A small mistake at the start of the process could magnify over time, turning a research project into a global threat. Consider a historical parallel: the Apollo missions. When astronauts first brought moon rocks to Earth, NASA enforced strict quarantine rules. Scientists worried about unknown lunar microbes. Even though the moon seemed lifeless, the rocks were sealed, and the astronauts were isolated for weeks. In hindsight, this level of caution was unnecessary because the moon had no life. But if they had been wrong, those precautions might have saved the planet. With an interstellar object, the uncertainty is far greater. The source is not just another body in our solar system, but an entirely different system, shaped by unknown chemistry and conditions. The need for containment is orders of magnitude higher. There is also the risk of missing hidden information. If 3I Phi Atlas contains evidence of past life or technology, we might fail to recognize it. Alien structures might not resemble anything we expect. For instance, A self-replicating machine could look like a lump of crystal. A form of life could be microscopic or based on entirely different principles. If we only search for familiar patterns, we could overlook critical discoveries. This would not just be a scientific loss, but a strategic one. Misreading the evidence could leave us unprepared for future encounters. To guard against misinterpretation, we need diverse perspectives. No single group or nation should control the study of an object. Like 3 Phyalus, multiple teams using different methods can reduce the chance of collective error. Open sharing of data is essential. If information is kept secret or restricted, mistakes may go unchallenged until it is too late. At the same time, transparency must be balanced with security. Some findings might need to be handled carefully to avoid public panic or misuse. Misinterpretation is dangerous because it multiplies risk. A wrong assumption at the beginning shapes every step that follows. If we underestimate the hazards, we may skip vital precautions. If we overestimate them, we may act with fear and aggression. In both cases, the consequences ripple outward. The safe path lies in acknowledging our ignorance and preparing for a wide range of possibilities. With an interstellar visitor, there are no second chances. Once the object is gone or the sample is released, the effects cannot be reversed. Every decision must be made with the understanding that we are dealing with the truly unknown, where even small errors can have cosmic consequences. The arrival of 3i Phyatlas creates a rare and valuable opportunity for science, but it also creates a potential flashpoint for conflict. A piece of material from another star system carries information that no nation has ever possessed. The first country or organization to capture and study it could gain enormous advantages. These advantages might include new technologies, new sources of energy, or even biological discoveries that could change the balance of power. When the stakes are that high, cooperation becomes fragile. History shows that when powerful resources are at play, competition often turns violent. Imagine 2 spacefaring nations with rivalries on Earth. Both track 3i Phyatlas as it approaches. Each wants to be the first to send a spacecraft to intercept it. Building such a mission requires money, skilled engineers, and fast action. Even if both nations succeed, only one can arrive first. That first contact matters. Whoever retrieves samples or data before the other gains a strategic edge. The losing side may feel pressured to act aggressively to prevent that outcome. This could lead to interference, sabotage, or even open confrontation in space. While a battle over a comet might sound far-fetched, tensions between countries have flared over far smaller issues in the past. Consider the Cold War as an example. The United States and the Soviet Union competed fiercely over space exploration. Each side viewed success not just as scientific progress, but as proof of superiority. Landing on the moon was more than a technical feat. It was a statement of power. Now imagine that instead of a barren moon, the prize involved unknown alien materials. The stakes would be higher, the secrecy greater, and the mistrust deeper. A mission to 3i Phyatlas could easily become a contest of survival rather than exploration. The competition would not stop at the point of interception. Suppose one nation successfully collects samples. The question of who controls that material would become urgent. Other nations might demand access, arguing that the object belongs to all humanity. The collecting nation might refuse, citing national security. This could trigger diplomatic crises or even military action. In a worst-case scenario, a state might threaten force to seize the samples. Such a conflict would not only risk war on Earth, but also damage future efforts to explore space safely. Secrecy adds another layer of danger. If a government believes the material from 3i Phyatlas contains potentially game-changing technology, it may hide its findings. Even peaceful nations might withhold information, fearing misuse by rivals. This secrecy breeds suspicion. Other nations, seeing a lack of transparency, may assume the worst. They might accelerate their own programs, building weapons or defensive systems in response to imagined threats. This cycle of mistrust can spiral quickly. During the nuclear arms race, both sides stockpiled weapons far beyond any rational need, driven by fear of being outmatched. A similar race could unfold over alien material, but with even less understanding of the true risks. There is also the possibility of deliberate weaponization. If the material from 3I Phaeatlas includes exotic chemistry or unknown biological agents, it could be turned into a weapon. Even a small sample might have properties that make it extremely dangerous. A toxin unlike any found on Earth might bypass existing treatments or defenses. A self-replicating molecule could spread uncontrollably if released. The first group to weaponize such discoveries would gain terrifying power. Knowing this, other groups would feel compelled to pursue their own weapons programs. The result could be an arms race with stakes, beyond anything humanity has faced. The race for control would not be limited to nations. Private corporations, scientific organizations, and even non-state actors might seek access to the object. A private company with advanced spaceflight technology could attempt to claim 3I Phaeatlas for itself. Governments might then intervene, fearing loss of control. Criminal groups or extremist movements might see an opportunity to steal material for profit or ideology. Each new player adds complexity and risk. A single theft or act of sabotage could trigger cascading consequences. Space treaties exist, but they were written decades ago when these possibilities were science fiction. The Outer Space Treaty of 1967 prohibits claims of national ownership over celestial bodies, but it does not address the practical issues of who controls samples or data, nor does it provide clear rules for military activity in space. As a result, nations might interpret the law in self-serving ways. Without strong agreements, disputes are likely to escalate rather than resolve peacefully. Even peaceful competition can lead to dangerous outcomes. Suppose two rival missions are launched at the same time, each aiming to collect material. Spacecraft traveling at high speed in close proximity could collide. A crash might scatter debris, destroy equipment, or even injure astronauts. The loss of a crew could inflame tensions on Earth, with each side blaming the other. In such a charged environment, an accident might be mistaken for an attack. Miscommunication could lead to escalation before facts are clear. The potential for conflict extends beyond the initial encounter. Suppose one nation uses information from 3I Phaeatlas to develop new energy sources or propulsion systems. These breakthroughs would disrupt global economics and military balance. Countries left behind might feel desperate to catch up or to prevent their rivals from gaining unchecked power. This desperation could drive reckless policies, including preemptive strikes or sabotage. History offers many parallels. The development of nuclear weapons reshaped international relations overnight. Entire strategies of war and peace were built around their existence. Alien material could have an even greater impact because its properties are unknown and potentially more transformative. The competition for 3I Phaeatlas might also accelerate destructive technologies indirectly. Even if the material itself is not weaponized, the rush to reach it could push nations to expand their space militaries. New rockets, satellites, and defense systems would be built at breakneck speed. Testing might be rushed, safety overlooked. In the scramble to gain an edge, mistakes would happen. A malfunctioning weapon or failed launch could cause disasters both in space and on Earth. The more complex the systems become, the more ways they can fail. Consider a scenario where two rival nations develop powerful new propulsion systems to intercept interstellar objects. These systems could later be repurposed for military use, such as delivering warheads or disabling satellites. Even if they start as peaceful tools, the line between exploration and warfare is thin. Once the technology exists, it cannot be unmade. Other nations, fearing vulnerability, would build their own versions. Soon, the skies above Earth could become as contested as its surface, with every satellite a potential target and every rocket a potential threat. The worst-case scenario combines all these risks. A fragment of 3I Phaeatlas is captured and hidden by one nation. Rumors spread about its contents, feeding fear and conspiracy theories. Rival powers mobilize, preparing to seize the fragment by force. Militaries posture in orbit and on Earth. A misunderstanding sparks an exchange of weapons. Amid the chaos, the fragment is damaged, releasing dangerous material into the atmosphere or space. What began as a scientific mission ends as a global catastrophe, caused not by the object itself, but by human ambition and mistrust. Preventing such outcomes requires foresight and cooperation. Nations must agree on rules before the next interstellar visitor arrives. They must share data openly and build joint missions rather than competing ones. This is difficult in a world where rivalries run deep and resources are limited. Yet the alternative is a future where every new discovery becomes a trigger for conflict. 3. Phaeatlas is not just a rock from another star. It is a test of whether humanity can handle the unknown without tearing itself apart.